Hello everyone, this is lecture 3 and it is chapter 5 in the textbook. As you know, we have reviewed the chapter 1 and chapter 2 of the textbook, but right now we are continuing with the chapter 5 here. We are not gonna go over with the chapter 3 and the chapter 4. These are the parts for revision of the all topics you have seen in the probability and the statistics courses. So I suggest you to review these topics, then you can apply the statistics knowledge in this course as well. Right, let's continue. Here in this chapter, we are gonna go with the basic statistical process control tools. And these tools are comprising 7 techniques. One is histogram, or it can be stem and leaf plot. We are not gonna talk about this, technique and this graphical visual aid. You have already know what is histogram and stem and leaf plot. If you don't know that, I'm 100% sure you know that, but you can check chapter 3 and chapter 4 of the textbook. Also, you can review your probability and statistics course lecture notes. Second is the check sheet. 3, Pareto chart. 4, cause and effect diagram. 5, defect concentration diagram. 6, scatter diagram. And 7, maybe the most important one, is the control charts. Here we are going to talk about from the check sheet to the scatter diagram, but we are just going to give an introduction on control charts because we are going to deeply get into the control charts in the next chapters as well. All right. So why are we using statistical process tools? We are using these process tools to achieve stability in the processes. So to achieve stability in the processes, so we can reduce the variability, then we can improve the capability of the process, we are going to use these tools we have, the statistical process control tools. They also called as Magnificent 7, and these tools are technique tools. Okay. The capability means, in the context of quality improvement, is the reducing variability around the target. So we are reducing the variability in the dimensions, the quality dimensions, quality aspects on the product's quality characteristics. Okay. Before getting to the techniques, the details of the techniques, to talk about the causes of variation. So we said we need to reduce the variability so we can improve the quality. And to improve quality, we need to use statistical process controls. But what is the variation? Which causes are resulted in the variation? So we can categorize variation into 2 parts. The one is chance causes of variation. The other one is the assignable causes. Chance causes are also called as common causes, and assignable causes are called as special causes. Chance causes mean like the random causes, and they are inherently in the process, so we cannot do anything about it. And if there are just common causes present in the process, it means the process is in statistical control. But besides common causes, if we have assignable causes as well, it means that our process is out of control. Why? Let's look at this figure. Here we are seeing some time frame. It starts 0 to the third time frame, T3. And here, from 0 to T1 time period, we have no assignable causes. We have just random common causes. And these causes are inherently in the process. And these common causes of variation actually comprises the small random things in it. This small random variation adds up the total common causes, and we can neglect these causes because they are random, and we cannot eliminate them because they are inherent in the process. So we are just focusing on the assignable causes. So assignable means we can assign some causes for this variation. So if we can assign, so we can eliminate them too. Okay. So in the 0 to t1 time period, we don't have any assignable causes. We have just common causes. So as you see here, these are the specification limits we have, and this is the target nominal value of the quality characteristics we have. And there is no out of control points here. It seems there is nothing going wrong here. But after T1 period, there exists one assignable causes, and it shifts our target value to the right side here. The shifted mean is here anymore. It's not in the center line. It is shifted to here. Then we have two assignable causes. Then we have three assignable causes, and it is shifting our mean, from right to left, and also our variability is getting larger. So we are exceeding our standard deviation here. So this is the shifted mean, mu1 after t1 period, and this is mu2. It is the shifted mean after t2 period. And here we are seeing that our standard deviation is as well greater than the null standard deviation, and which is here. This is the low variability around the target value, and after some assignable causes are present, the variability is getting larger. So about assignable causes, what can be assignable cause? So if we can give some examples on it, there can be improperly adjusted machines, or it can be operator errors, or it can be defective raw material. These kind of things are the assignable causes, and we can eliminate them because we can adjust if the machine is improperly adjusted. So we can cause operator errors if we train operator or if we change the operator. So we can eliminate defective raw material if we do not put these defective parts, defective raw material into the process. Okay, but about natural variability, which is common cause, or it can be also called as chance causes, we cannot do anything about it. It is like background noise. All right, but it doesn't harm us actually in the quality terms. The aim of the statistical process control is to detect the assignable causes so that we can take corrective actions. Then we can reduce the variability so we can improve the quality. Let's talk about control charts first. The control chart has three components. The first is the central line, and we have two limits in each side of the central line. One is the upper control limit, and the lower side, it is lower control limit. But be careful, okay? Be careful, everybody. These are not the specification limits we have talked about in the chapter 1 and chapter 2. These are not the specification limits, okay? So in next chapters, we are gonna make a relation between specification limits and the control limits. Okay, it is out of scope for this lecture, but these control limits are not specification limits we are talking about. These control limits just showing us, how can we make a derivation from the target value, so we can be in statistical control situation. All right. So these limits will define our limits for the in or out of statistical control situation. Okay, so then in next chapters also we are gonna define or how can we set these control limits. It is up to us again, but there are some general guidelines for setting these control limits. So for a typical control chart, we have three components: central line, lower control limit, and upper control limit. And these are the limits we have. And this is central line. So what about these points then? These points are the samples we are taking from the process output. Okay, so there are some inputs through the process, then the process is doing its job, its thing. Then we have some output, and let's say the outputs are the products, and we are looking at specific quality characteristics in these products, and we are measuring these quality characteristics. All right, let's assume that we are measuring them, and we are not measuring all of them, but actually we can also measure all of them, but let's assume that we are measuring the sample to sample. Okay, we are taking sample, then wait, I don't know, for example, wait for an hour or wait for a half hour, then we are taking another sample, then another sample, and another sample, and we are taking the average of this quality characteristics value on these samples, and these points are given these values actually. Okay, it is not necessary, it is not a necessary thing to draw these lines. We can just put the dots here, but to read easily, in order to read easily the control charts, this is just a common procedure, common thing in the industry. They're drawing lines, but lines actually does not mean anything in the control charts. The points are representing something. These points are representing the samples quality characteristics value. It can be average, it can be a range. So we are gonna talk about this things later, but let's assume that, for example, we are just looking at an average value in the samples. Okay, these dots represent the samples averages, for example. And here, for example, in this chart, this process is in statistical control. Why? Because we do not have any out of control points, right? Above or low, the beyond of the control limits we have in the control chart. All right, so what are we gonna do if we have an out of control point? In this situation, we need to take corrective actions. We need to identify the assignable causes resulted in this out of control points. Then we need to take action, then eliminate it. Then again, we are trying to balance our process. It can be again in statistical control. We use this control chart as a monitoring tool actually. When we observe an out of control point, it means we are detecting an assignable cause. Then we are identifying it, finding it, what is causing this out of control point. Then we are eliminating it. So we are reducing the variability. Why? These out of control points will shift our target value actually. For example, these out of control points can be larger, much more. Then our nominal value will be shifted, and variability will be increased. So we are eliminating these assignable causes resulted in out of control points. Then we can reduce the variability and make our process again in statistical situation. All right. And also I want to talk about the connection relation between control charts and hypothesis testing. Hypothesis testing, you are going to remember from the statistics course. What is hypothesis testing? We can have a null hypothesis, which is here in our context, And we have an alternative hypothesis. In the control charts, our null hypothesis is the process is in control. All right? So to mu1 is here means, the mu1 value, the mean value in the, future samples we have. It can be, we can take mu1 here or mu1 here. Doesn't matter, all right? Mu1 is here means the next situation we are taking the mean value, okay? And mu null is here is the set value for the central line, the nominal value. So if the process is in control, it means that the next mean we are gonna calculate again in next samples will be equal to the mu null value, the original value we have, it is central line. The alternative hypothesis is here says process is out of control. Mu1 is not equal to mu null. It means that in next samples, the mean value will be drifted away from the central line we have here, okay? It's gonna be, for example, we are gonna get out of control points, for example, here, then our shift will be drifted away, for example, here, right? Because we are gonna have data here and it will be shifted our target value to the lower values, all right? The mean will be shifted. So we are using control charts, and in this manner actually we are testing our hypotheses, all right? So in hypothesis testing we have some errors, right? Like type 1 error, it is alpha, and type 2 error, beta, and alpha means in the context of control charts. We conclude that our process is out of control when actually it is in control. And type 2 error beta is saying our process is in control when actually, truly, our process is out of control. All right, these are the errors, and you can make a relation between the original hypothesis testing we seen in the general, not the original, just general hypothesis testing we have seen in the statistics course, and in the context of control charts, the hypothesis testing we have. There is a relation between them, all right? And if we get a point in the control limits, between control limits, it means that we are failing to reject null hypothesis, okay? So the process is in control. If we see some points out of control limits, actually it means that we are rejecting the null hypothesis. So the process is out of control, all right? We are rejecting null hypothesis. It says process is in control, but we have observed some value out of control limits, so we are rejecting it because we have some out of control points. Okay, let's continue with an example. Here, in this example, our quality characteristics is the average flow width. If you are interested in, for this example, you can check textbook and read the original example. It is wordy, I'm just skipping the introduction part of the example. I'm talking about the results, the example actually, results of the example. Our quality characteristic is here in this example, average flow width, okay? There is an example of quality characteristics, okay? And here we are seeing, for example, the fourth sample average, and it is 12th sample average, and it is 20th sample average, and something like that. And this is the target value, is the grand average of them actually. And each sample has 5 wafers, and wafers like products, okay? Just assume that these are the products we have. Each sample has 5 products in it. Okay, so process mean is 1.5 microns. This is the mean, the mu, okay? And the process standard deviation is we know the standard deviation, the population standard deviation, it is 0.15 microns, and we know the population mean, it is 1.5 microns. And we see all of the points, all of the samples are in control in the between the control limits. So we can say that this control, this process is in control, statistically in control. So how can we determine the control limits then? We have mean and standard deviation. We can use this method. We can calculate them like that. So we know the population standard deviation is 0.15 microns, but we need to take the sample standard deviation because we are taking samples from the population, right? So we are dividing the population standard deviation to the square root of the sample size, and it is the sample standard deviation value. So we need to determine a control limit by using the standard deviation we can say that if the type 1 error probability, what was the type 1 error probability? Type 1 error probability says the process is out of control when actually it is in control. So there is a probability, there is an error probability we have, and we can decide our control limits by considering this error here. If we want to reduce it, we can choose, for example, 5 sigma. But maybe the error is getting lower, but actually the type 2 error probability is getting larger, right? So we are gonna say the process is in control, actually it is out of control. So we need to take a balance, and industry, they are using the 3 sigma levels, okay? This is just like a general approach, but it is up to you, it is up to the quality engineers, it is up to the company. Okay, you can change this value, but in this course, we are gonna assume that the control limits will be set by the 3 sigma levels in the above side and in the below side. These control chart models is called as Shewhart because Shewhart is the one, introducing these control charts in the quality management. Okay, so we are assuming the statistics we have as a normal distribution, so we can use these sigma levels, right? Okay, because you're gonna remember that in normal distribution, these are the levels we can, set by from the deviation from the central tendency here, right? We can use normal distribution to define these limits, and we are assuming that the statistics we have, these statistics, for example, the average of the samples, for example, and we assume that these sample statistics are normal distributed, so we can use this kind of limits. Okay, and Shewhart control chart model says the central line will be the mu W. W is here. Statistics can be average, it can be range. Okay, we're gonna also see the range control charts. All right, so upper control and lower control limits can be set by the deviation from the target the central line value. Okay, and L is the distance of the control limits from the central line. And we said that in industry they are using 3 sigma levels. This will be the 3 in general approach. Okay. So how the Shewhart control chart works? We are gonna take samples. Okay, then they are gonna work. Otherwise, if we do not take samples, our control limits will be wider because we are going to use the population standard deviation. But in the samples, we are going to reduce the standard deviation by the square root of the sample size. So limits are dependent on the sample size. Okay, if it's larger, if we use larger sample sizes, our limits will be narrower. All right. After using the control charts, we need to identify the assignable causes, then eliminate them so we can improve the process. Okay, so the taking action after observing out of control points is the important part of the control charts using. Okay, so this is a kind of a typical roadmap. How can we use control charts generally for a process? So here, guys, for example, if are getting out of control points, we are going to detect the assignable causes, then we are going to identify the root cause of the problem, because otherwise it will be just a cosmetic solution. It will be just a superficial solution. So we need to get rid of the root cause, then we can make a sustainable improvement in the process. So this is, for example, an example of out-of-control action plans. We are taking out-of-control action plans after observing out-of-control points, beyond the control limits. So this is just a typical example. You can pause the video and then read it. It's just an example given in the textbook. Okay. All right. Let's continue. But it is important, all right, everybody. This is very important. The out of control action plans is important thing, and it is changing. It is up to the situation we have. Okay, here it's just an example. Okay, but in your situation it can be different. But just make sure that you are identifying the assignable causes. Then you are getting rid of the root causes of this problem, then you can make an improvement in the process. And your out of control action plans must do these things. Okay. So control charts also can be used as estimating the process parameters, and then we can determine the capability. Do not worry about what is capability, process capability here, because we are going to discuss these things in next chapters as well. So also we have two general types of control charts, and it is categorized by the data type. If our data, if it's continuous, we are using the control charts for variables, okay, like X bar chart, range chart, R chart. If it's attributes, or if it's discrete, like counting data or it's percentage data or something, it's called control charts for attributes. And we are using the C chart and the other charts as well, but we are going to see those charts in next chapter 7. Okay, do not worry about it right now. And also for control chart design, the selection of the sample sizes, the control limits, and the sampling frequency is also another important part for the control chart. And it is up to the owner of the process. It is up to the quality engineers. Okay, so you need to determine the sample sizes, determine the control limits, and determine the sampling frequency. And there are some trade-offs between them. Okay, and let's, for example, we don't see here, but maybe in the next class we are going to discuss it. Okay. And what about the types of process variability? Here we are seeing 3 examples. In first example, we are seeing a random pattern, right? It is up, down, up, down, up, down. And it is called, in this situation, it's stationary and uncorrelated because the process is in control. This is the upper control limit, this is the lower control. There are no out of control points. This is stationary, around the target value. And it is uncorrelated because it is going up, down, up, down, up, down. There is no trend here. But in the example B here, we see that maybe they're like around the target value and they are not getting out of control. But right now there is a relation between points, right? For example, here these points are going down and the successor of these points are going down too. So there is a correlation here, autocorrelation here. And about the C example, this is not non-stationary. This is not going around the mean. So it is going up, then down, and down again. So the mean is shifting to the lower side. Okay, these are different kinds of variability. Maybe these examples seem like they are in control, but actually example B and C types are not in control. Maybe there are no out of control points, but there are something going wrong here. Okay, so also we need to observe the patterns. Then maybe the control chart seems in control, they are not in control. Okay, so we need to observe the patterns. We need to know them. They must look like this. They must look like random. Otherwise, there are just some faulty things, in the processes. So we need to find them. We need to find these assignable causes, then get rid of them. So we need to make our process, not the process. We need to make our control charts seems like that. Okay. So how can we fix it? We are gonna see these fixing methods in part 4 of the textbook. Control charts are popular and important because they can reduce the rework and scrap and increase the productivity. Because control charts can prevent the later, indirect costs. So we are using control charts, so we are eliminating the causes, assignable causes, so they are not gonna be a problem in the next processes we have. And if we use control charts, we do not unnecessarily adjust the machines and the processes. So there's like a slogan here: if it's not broken, don't fix it. Okay, if control chart seems right, if it's in statistical control, do not make any adjustment, because there is no assignable causes here. There is just common causes. Maybe it shows some variability, but this variability comes from the common causes. You cannot do anything about them. So do not adjust anything, just continue your work. Okay. Also, control charts provide diagnostic information for us, the patterns like that, so we can diagnose our problem, then we can solve it. Also, control charts provide information about the process capability. We can estimate the parameters, then we can formulate our process capability, and process capabilities is a very important metric. Okay, we are going to talk about process capability in next chapters, and it is very important for management. Okay, just keep in mind process capability and process capability ratio. These kind of metrics are very, very important for the management side. Okay, do not worry about them. We're gonna see how we compute this process capability, and what is the definition of process capability, how can we interpret this process capability things in next chapters. Not worry about them. So choices of control limits, we had said that the 3 sigma levels, are like common in industry, but in some European countries like UK, United Kingdom, they are using the probability limits, and probability limits, I'm not gonna get into the detail because it's not relevant for our case. They are using the probability level. This is the 3 sigma level, so we have also some probability levels like alpha level here, right? And it is 0.001 is used in those countries, and it is equivalent to actually 3.09 sigma control limits. Okay, about the sample size and sampling frequency. When we choose the sample size, we must keep in mind the size of the shift we try to detect. So the sample size is affecting the width size of the shifts we are trying to detect here. So we will take frequent sampling, but it is not economically viable. It makes some costs for us, and it can be detrimental for us. So we are just gonna take some samples. Also, we can, for example, take small samples with shorter intervals, so frequently. And also we can take large samples. The sample size will be large, but we are going to take these samples with longer periods. So it's not going to be frequent sampling. It's going to be infrequent sampling. So this is like a trade-off. Okay, we can use this trade-off and decide. But in industry, if you produce high volume products, so the small samples with the shorter intervals is the most used one approach. Okay, and to determine the sample size and the sampling frequency, we can take into consideration some terms. Okay, but these are just the considerations. Okay, so average run length is the one of them. We have two average run length value. We are going to have two average run length value. The first one, the average run length null, and it says the average run length for the in statistical control situation, and average run length one will be the out of control point situations. Okay, these are different average run length computations. Be careful about it. So here, average run length, we are going to calculate the 1 over p value. What is it? The p is the probability that any point exceeds the control limits. These are the control limits we have, upper control limit and lower control limit, and we have some probability for that. Okay, in control processes, we have a probability for type 1 error, right? What was the type 1 error probability in the quality terms? It was saying say that the process is out of control. Actually, it is in control. And if we interpret this, sentence into our figure here, so we are going to observe some, samples out of control limits, but they are just random. Actually, the process is in control, but we are observing these points because of randomness. Okay, lots of the samples are in this range, but some of them are showing us the out of control points. But there is a probability for that, and this probability is the alpha, the type 1 error probability. Okay, so we say that in statistical control processes, if the process is in control, the average run length will be the 1 over p, and p is the, in 3 sigma levels, it was 0.027. So for the 3 sigma levels we have, okay, here and here, the shaded region here and here, if we add up these regions, the probability we have, actually, it is the type 1 error probability alpha. You can remember those calculations, those things in statistics course. If you are not familiar the things I'm talking right now, okay, alpha, type 1 error, something like that, please check the statistics lecture notes, okay? So the shaded region probability is here 0.027. So 1 over that probability value, it is 370. So this value says us, in average, in expectation, we expect that after taking 370 samples, we are going to observe an out of control point in the process which is in control. Okay, this observing this out of control point, actually it is random. It's not about assignable causes here. Okay, because of the randomness, and we assume that this randomness is the normal distribution, is in normal distribution, we have a probability that we are going to observe some out of control points after some samples, and actually they are not true, they are not the things resulted from the assignable causes. These are resulted from common causes, but they are there. And we expect that these out of control points will occur every 370 samples. This is the expectation number, okay? It can be after 2 samples, for example, but in average it is 370. We expect these numbers. This is for the in control processes. this average run length will tells us how much or what sampling frequency we need to use. Okay, we need to take into consideration these average run length calculations to make a determination in the sampling frequency. But about these computations, there is some criticism, because observing this out of control point in the first time, it is the geometric distribution. Okay, so in the geometric distribution we have a skewed, right skewed distribution, right? It is like that. This is right skewed distribution, geometric distribution, and this is the mean value we have, 370 in the geometric distribution, and as well with the standard deviation, it is again 370. So it is very high value. There is a huge variability on it. So in expectation, maybe it is 370, but the variability is also 370. So our values will, vary. More likely we are going to observe average run length values here, and we are not going to observe these values because these values will be in the lower probabilities. Okay, but it is just the p-value when it is very low. Okay, so another computation, it is average time to signal, and average time to signal says us a fixed interval we can take a sample, and it is just multiplication of the average run length with a time period. For example, if the sampling frequency, if we take the samples for 1 hour, it means that we are gonna get a false signal. The false signal here out of control points observation will be in 370 hours. So this average run length null was the processes is in control, but if we have an out of control process, so what can we do? What are we gonna use? What formulation we are gonna use? We are gonna use the formulation here. If this is the average run length 1, and it represents the out of control processes average run length, and it is 1 over 1 minus p, and 1 minus p here is the beta risk we have, and beta is calculated already in the OC curves, operating characteristics curve, and you're going to encounter these curves in next chapters as well. And do not worry about these formulations, okay? Because we need to also, we can directly calculate the beta risk values. We have a formulation for this, but we are going to use the OC curves, OC curve diagrams, and after getting the beta risk value, we can calculate the average run length for the out of control processes. Okay, so we are going to use average run length 1. Why? Because we need to detect the shifts in the mean. So we are assuming here the process is out of control, so there is a shift in the mean, and we are trying to detect this shift. So average run length will say something about us, in what sampling frequency we can detect this shift, so we can take a corrective action. So suppose we are using a sample size of n, it is 5, and that when the process goes out of control, the mean shifts to 1.725. It was 1.5 microns, right? So the shifted mean is 1.725 microns. From the operating characteristics curve here, we find that if the process mean is 1.725 microns, if the mean is shifted these values, okay, the probability of average x, it is the quality characteristics we have, falling within the control limit is approximately 0.35. Why? It is low, right? It is very low, the falling between the control limits probability, because our mean is shifted. So the mean is shifted, so the point, the samples will be the out of control limits mostly. But we are going to observe also in control samples, and there is a probability for that, and it is given in the operating characteristics curve. And do not worry about it. How can we, calculate this, all of these values? There is a calculation computation for this, but right now just focus on this operating characteristics curve. We are taking this data here, the falling between the control limits probability, it is 0.35 if the mean is shifted that value, okay? So the average run length for out of control processes will be 1 over 1 minus p again, and p is reduced here, it is 0.35, and it will be the 1.53. So here, actually, it tells us something. It is telling us out of control processes, we are gonna get an out of control dots, the samples, in every 1.53 samples. This is the expectation again, okay? This is the average value, this is the expectation value. It is decreased, right? It was 370 for the in control statistics, statistically in control processes, because there was no shift in the mean. But here we assume that the mean is shifted into a higher value. So the points, the samples will be out of control points much more, actually much more. So average run length will be the 1.53. So it will be reduced to that value from 370 to the 1 point something. So we are gonna get much more out of control samples. Okay. So again, guys, these calculations are wrong. So I just, raised them in some way. Okay. Do not use this. This is the right calculation. Okay. And do not read that part. Okay. But here, I'm taking your attention here. This was a calculation for 5, if the sample size is 5. If we increase the sample size to the 5 to the 10, our average run length will be much lower. Why? Because the falling between control limits probability will be reduced. Why? Sample size is increased. So we are getting so much information. So out of control points will be much more than the situation we have a sample size of 5. Okay? So to conclude that part, if we increase the sample sizes, we can detect shifts more easily. Okay? This is the essential part given here. So let's continue. So this is, two different designs. In one design, the sample size is 5, and in design 2, sample size is 10. So we can, generate a sampling frequency technique here, a procedure. For example, sampling frequency can be 45 minutes. Average time to signal will be same with the design 2 at this level. For example, average time to signal for design 2, it is 1.11 hours, because average run length 1 was the 1.11 samples. We are multiplying this value with a time period. It is 1 hour, and it is 1.11 hours. So it is like same if we are taking samples in every 45 minutes and the sample size is 5. The probability detecting shifts, okay, is determining how much sample size you use. And also it determines your sampling frequency. You need the look at those kind of information, average line length and average time to signal, these values will say something about your determination on sample sizes and sampling frequency.